Okay. So Module 3. This is where we'll get into some more advanced topics. Building on top of what we talked about earlier today, we're going to get into some discussion about container storage. And then we'll move on to that into some Docker internals. Just again, kind of getting into a little bit of the details of how containers work. And we'll cover some best practices and considerations that you may want to adopt yourselves as you explore Docker and use it in the real world. And then some Docker pro tips, which is mostly about covering some interesting tools out there to help you along the way. So we'll begin with Docker container storage. We've talked about the processes and the isolation, and we've been able to get the processes connecting across the network, even across multiple hosts. But now there's obviously use cases where we want to persist the data in those containers and even share the data across containers, and that's what this will be about. So some different types of storage that are available through Docker are the very first thing that you see when you get into a container is the local container storage itself. That read-write layer that I described, that is a form of storage, and it's only for that container. It's also possible to mount volumes and directories and files from the host and then have those exposed inside of the container. And so you penetrate that read-write layer, and now you're affecting what's on the host. There's also a concept of Docker volumes, and I think I had misspoke earlier today when I said about Docker 110 and networking. I was actually thinking about the named volumes support. That's what's new in Docker 110. To be able to have volumes is something that's been around for a little while, but they've recently had the ability to name them. And then there's also the ability, as with networking, to have volume plugins, so that way you can have extensions to the storage component. For some of these, there's different backends that you can choose. For example, if you mount a directory from the host, that could be stored locally on the host, ext, ZFF, whatever sort of storage you have there. You could be on NFS. It could be mounted from some other location. But then there's also the ability for some of these solutions to use cloud solutions, such as AWS Elastic Block Store. And then the one I'm going to be demonstrating today is GlusterFS, using a Rancher Convoy plugin for Docker. So we'll just take a quick look here at volumes so you understand what they are before we get into multi-host storage. So here we've echoed a string to a test file on the host. So this file only exists on the host. I'll show you what directory I'm in. It's a temp directory. So if I do Docker run, I'm going to remove the container when it stops, make it an interactive demo here. And I have the -v /temp volume demo. That's the current directory I'm in. And I'm mapping that with a colon to /data, which is a directory inside of the container. And then I'm running my Ubuntu image, and then I'm telling it I want to run a bash shell. So now if I cd into this directory inside of the container, I see my test file that I just created outside of it. So now I actually have one directory in there that is not persisted on that read-write layer. It's actually on the host. So I can look at it. I can see that there's something in the file. I can modify it. So I'm going to echo just a string and give it the host name that's currently in there, and then have that appended to the test file. And so I exited the container, and now on the host, I can see that the file is modified from inside of a container. And the container is destroyed. It's gone now because I used the --rm command. So I'll do another experiment here. I'll do Docker run, and I'm daemonizing it. I'm running a named Ubuntu image called Docker Camp, but I'm now doing -v /data. I don't have that colon there. And what this is going to do is this is going to create a Docker volume. It's not going to bind mount, which was the one that I just did before. This is a volume that can be shared between containers, but is not accessible from the host. It's just living in Docker land, right? It's just a storage directory inside of Docker. So if I start a container here, if I exec into the container, a shell, I can see that I have a data directory. And there's nothing in there, but I'm going to echo the string here and append it to a new file. I'm going to exit out of that container. And I'll start up a second container from this, and I'm doing this --volume from and then the named container that I created before. And what that's going to do is bring in all the volumes that were created with that -v that I showed you in the first container into the second container. So they're sharing now this volume, this Docker volume between the two containers. So if I cd into this data container in the second container, and I can see that I have that file there now. And just to show you, the appended from within is the host name from that first container, but I did host name here in the second container to show you I'm definitely in two different containers. So now take a look at what volumes were created. We can use the docker volume ls command. And then here we have one volume, which was created with that -v/data command option. And it's a local driver. This is the plugin sort of thing that we were talking about a moment ago. And the volume name, by default, is this cryptic string because it was just randomly generated. We didn't create a named volume. We created a volume on the fly when we added that to the docker run command. We can remove the container that created that. And we can start up another container and specify that we want to use a /data volume. But something interesting will happen here. We have two volumes. And that's one of the big things that before named volumes came along, and I'll show you how those work, that people would create a container and call it a data container. You may have heard about this if you've looked at Docker recently. And they would then just have that container does nothing, and then they would refer to this volume based on the name of that container so they could correlate it to a common name everybody could use. You don't need to do that now that we have named volumes inside of Docker. But if you didn't do that, what would happen is every time you start a container with what you might think you'd be sharing a name for a volume /data, you get a new volume every time, and they would not be sharing data. They would all have their own volume instances. So let's exec into this other container here, and just to show you that the data directory exists, but there's nothing in it. So we'll start up another container. And this time, we're giving it a named volume. So this time, rather than just the /data, we said myvol :/data. And this is how you specify a named volume in Docker. And so when we show you in a second, you'll see that there's a my volume now for the name. Docker tells the difference between a local host mount based just solely on that /. So if it was /myvol, it would think that you're trying to mount a directory called myvol on the host. The omission of the / tells Docker that you want a named volume. So that's one small little thing that can be a gotcha. So we'll create a file here in this named volume. We'll call it named volume file. And just to show you, on the host, nothing's changed here. This was the test file that I initially created that I mounted, but we don't see any of these named volume files or anything because they're only in Docker volumes. Now if I do docker volume ls, we see the two that were created randomly from those two other containers, but now we have this third one here, myvol, which we explicitly named. Now, when we destroy a container and recreate one, as I'll show you, we have this one running still. I can run a container and then specify the same name and then mount that container by name. So now I can actually see the same data shared between different instances of containers. And again, the host name is different from the first time when I created it and the second time I created it. I could destroy all the containers and then recreate a new one with that named volume. And unlike that unnamed volume, I would be pinned to my volume. I wouldn't create any additional containers like I did that first time, or additional volumes. So we have this volume local to the host, but it doesn't allow you to span hosts, right? And that's another problem that we have that just works with the networking. One solution is to use a distributed file system like Gluster and then put Docker on top of it. And that's what I'm going to show you now. But first, I need to tell you a little bit about Gluster. You don't have to understand too much about its architecture. But it's a distributed file system, and it routes requests within a namespace in Gluster. So you can create a pool of data blocks, as they call them. It's really just blocks of storage. And route a request to a file through the Gluster network. And so it'll find out, okay, which host has the right block. But it also supports replication, so you can have a fully replicated data store if you wanted to across all hosts. And there's really no routing except to always the local one. It's been around for a while. It supports GeoWare replication, but it scales up to petabyte scale. This has been proven in a lot of academic institutions that have used this at scale. It's currently supported by Red Hat. They purchased the company that had initially created the source code for this. And it works with the Docker Volume plugin, Rancher Convoy. Rancher Convoy can also support NFS, but there is a GlusterFS variant. And as I mentioned, we can use it with containers. So what I'm going to show you here is how to deploy GlusterFS on Rancher. So first we need to create the Gluster cluster. Kind of rhymes. And there's a catalog entry for GlusterFS. So we're just going to use what they have out of the box. It's going to create 3 nodes, that's what the description said, and a volume. These volumes are different from Docker volumes. It's a Gluster volume. We're going to name ours primary. And then click OK. And what it's going to do is create a stack, just like we did with Docker Compose. It already has everything in there that it needs to know to pool all the Gluster containers. And so it's spinning this up now. We see we have a stack called GlusterFS across our 3 hosts. And it's starting to spin up the first container for the GlusterFS server. Now the GlusterFS architecture, if I recall correctly, does do an elected master. So we'll see one of these hosts have a couple extra containers, which is the master, but then if that master would go down, it would re-elect another one, and then we'd see that container spin up on that host. The Sidekick containers there are what I mentioned before. These are containers that are starting up with that host. This is something that Rancher allows you to do, to say I want these containers to always start in the same host as the other container. And those containers are actually going to die pretty quickly because all they're doing is some initial setup. That's the way they've designed this, is that there's a couple of additional Sidekick containers that just do some initial config. So that's been spinning up, and we can see in the stack view, an alternate view, just to show you the Rancher UI. We have our tabs here for each one of the Sidekick containers, and we can see a little bit of information about the images, and then currently the scale, how many other images have started up. And the stack is still starting up. And this is the containers view, where you can see all the containers running within this stack and what the status is. So we're almost started. We have 2 out of 3 servers running. And up at the top there, you can see with a little spinny globe, it's saying it's waiting for the 3rd server to start up. It's still extracting the Docker image is what it's doing at this point. Okay, now it finished. There we go. Now it all started up, and we can start seeing some of the stats come in from these three hosts. So Gluster is not something that is Docker native. It's, like I said, it's a third-party thing. What we're going to do first is just take a look at Gluster itself, and then we're going to put the Docker component on top of it with the Docker Volume plugin from Rancher Convoy. So just like any other container, I went to a host here, and I'm going to Docker exec into this so we can take a look at Gluster. So we can see we have a couple of Gluster Docker containers running. And the server one is the one you can get into. I think they both have userland utilities, but we're going to exec into that one into a shell and run the Gluster command line interface. So now we're inside of Gluster itself, and this is where you configure all your volumes, the replication scale, how many nodes that they need to be on, all those different sort of things. So similar to the Docker volumes, there's also a volumes command here. We can list the Gluster volumes. Now what's going to happen when we get to this point is that this primary volume will actually store Docker volumes inside of it. So the terms are so similar that it may be a little confusing. It's just that the volumes for Gluster is just going to be a store for Docker volumes. So we can look at this. By default, what the Convoy catalog is set up for us is a Gluster volume that has 3 bricks. So there's 3 different hosts that have data storage in this volume, and it's set to type replicate up at the top there, type replicate. And so every file that's created on one of these hosts will be replicated to the other instantaneously. It'll be synchronized when it does that. And now we'll talk about Rancher Convoy. So we have a volume for Gluster. We have Gluster running. It really wasn't that hard to get it spun up and running. But the Rancher Convoy is the plugin that Docker will use to put the Docker volumes inside of Gluster. And this is managed through the Rancher UI and API. And you can spin it up in a Docker Compose as well too. It supports NFS, as I mentioned, as one variant of it, but we're going to use the Gluster FS one. So to get that going, we have, just to show you again, we have our 3 Gluster nodes running. And to install the plugin for the Docker volumes, we just come to the catalog inside of Rancher, the public catalog again, search for Gluster, and then go to the Convoy Gluster catalog entry. So here, there's really not much to set up other than just specifying what was that name that we first named the Gluster volume. We had named it primary. And then what's the service name that's also running as the Docker Compose service instance inside of Rancher. So we just say we want to start that up. And it's starting up the nodes for that now inside of Rancher. If we take a look at that, we can see that this one's a little bit more simpler. There's no sidekicks that get started up with these containers because it's a thinner layer just to provide a connection between Gluster and the Docker volume. So that other stack's starting up. Now there needs to be an agent on every host in order to support the Docker volume plugin on every host. So that's why we see one container on each host here to support this. But each one of those will talk to the Gluster agent that's on that host. So they don't necessarily have to go across the network once we start using this here. As you can see, they're downloading the images from Docker Hub and then extracting it. Some of them are starting to get started. Now there's a little bit of thrashing when this first gets started because I think they're trying to decide which one of them are going to be the master for the configuration. So we'll see some of them stopping and starting until it reaches kind of an equilibrium. So we're almost there. There we go. So now we have our Gluster Docker volume installed. And it's under the system stack. So there's user stacks and system stacks, and they're separated kind of like how Rancher OS did for system Docker and user Docker. Now, if we go to the infrastructure, we see a new item here under storage pools. We see our Convoy Gluster and our 3 hosts that are part of that. And they're all hosts that provide Gluster, because that's how we specified that, if you recall, when we set up the Convoy Gluster. We pointed it to that stack that had the Gluster FS on it. So let's add a container to leverage this. We're just going to call this one Gluster Test. And it's an Ubuntu image. We're just going to add a volume. So similar to how like we did on the command line, we're going to say my Gluster as the named volume /data. But the big difference here is that we're going to specify a volume driver, and we're going to call it Gluster volume. And this will tell Docker to use the Convoy Gluster plugin to implement this volume. So we started up that container, and it's starting up. We're going to clone it so I can show you how the data replicates across hosts. So we're just going to create another container, all the same settings pretty much, except we're going to make sure that this one starts on a different host. We put it on O3. The other container is running on O2 because that's where we started it. So this container is starting up, and we see Gluster tests and then another Gluster test. For good measure, just to clarify the demo here in a second, we're going to rename this different container to Gluster Test 2. So now what I'm going to do is I'm going to create a shell in each one of these. So they're running containers. I'm just going to create a bash shell in each one of them. And then I'm going to concurrently edit a file in both of these. So that way you can see how the data is being replicated across the network, across the storage plugin for both of these. So then we have Gluster Test and Gluster Test 2, 2 different containers. If I do ls, we see that we have our data directory mounted inside because that's what we specified as a Docker volume mount. It's mounted to a Gluster FS Docker volume. If I go into this directory, there's no files yet. On one container, I'm going to create a file. I'm just going to touch a file called test file. So there'll be no contents. It'll just create it. And immediately on the other container on a different host, I see that file appear. It replicated across the network that fast. Now, I'm going to show you that there's nothing in the file on the one host, and I'm going to append to the file on the other host, in the other container running on the other host. And we'll see coming back to the first container that now I see the contents written from the second container, replicated across that distributed file system. And just to show you that there's no special locking or anything like this here, I can append the file on the first host that was written from the other host, and I can see that on the other host. So really, either container can write to this file, and the file locking mechanisms are very similar to like NFS v4, and GlusterFS handles that for you. I can delete the file on one, and it disappears on the other. So I'll exit out of that. And in the Gluster, volume is visible through the Docker or through the Rancher UI as a named volume here, and we can see which containers have mounted that. So Gluster Test and Gluster Test 2 have both mounted the same volume underneath of the data directory. So let's do something a little bit more interesting though, right? Because that just kind of scratches the surface of what's possible when you have a replicating file system like that. Here we have a Docker Compose file. We have a web application up at the top. It's a public image I just pulled because it's good for a demo. It's called Compose Demo. And we've set it up here to link to a database, a Redis database. Then we specify the Redis database container itself underneath of it, a Redis image. And we've set this up so that Redis will run in a mode that can be replicated across different file systems, and multiple Redis can read from it. But what we've done is mounted a data directory. We've created a named volume called Redis_data, mounted it to the data directory inside of the Redis container, and then we specified that we want to use Convoy Gluster as the implementation for that, as the volume driver. And then finally, to finish out this demo here, we're going to use HA Proxy so we can move things around a bit. And so our last container is HA Proxy, a load balancer service that Rancher had provided. I showed you that at the UI before, but I'm doing it here just through the Docker Compose. We're going to expose port 5000 from the web application. We already know it's going to do the expose on 5000. We're going to map it to port 80. And then we say the link to the HA proxy is to the web instance. So we have HA proxy linked to web, web links to Redis. And we're going to specify a label here. This is where we get to some scheduling things we can do with Rancher. I've specified a Rancher host affinity label to say that I only want this HA proxy to run on a host that has a tag of role equals primary load balancer. And the reason for that is because as I stop and start things here, I don't want the load balancer moving around between hosts, because then I'd have to point to a different IP address. I want to make sure that this load balancer always is on the same host. So to show you just a little bit first what's in this application, this Docker Compose demo, it's just a Python application, creates a Redis instance. It expects a host named Redis. That exists because of the Docker Compose file. That container that's created in Docker Compose will be in the DNS as Redis. And we open up a port to it, and we're going to modify a value there. We're going to increment the hits number and then read it back. So it's a very simple application. Now if we go to Rancher here, just to show you, we have our 3 hosts here, Docker DSLab 02. For this one, we want to label this one as the primary load balancer to make sure that HA proxy always lands on this one. So we're going to create a label through the UI here, role equals primary LB. And there we see our label for this host now. And that will be used as part of the scheduling rules. Coming up to applications, we're going to go to stacks again. And just like we did the first time, we're going to create a stack. We're going to name this one My App. And then we're going to paste in that Docker Compose file that I just showed you. And just to highlight that real quick, it's the same contents that were on the slide. We'll hit Create. And it's going to start spinning up the containers. And again, it does this in order in terms of what the Docker link statements say. So Redis started first, then the web instance, and then HA proxy will start last. So Redis started pretty quickly, waiting for the web, and HA proxy is coming up. All right, so everything's up and running. Take a look at the infrastructure tab. We can see how the containers were distributed. HA proxy is on our first host, as we expected, because we explicitly told to via a label. And the other two wound up. Web 1 is on 03, and Redis is on 04. So our application is actually spanning hosts. So Rancher Networking is taking care of that for us for the connectivity. And if I go to this here, you can see, now that I'm hitting the app on the proxy port, every time I hit refresh, it was hitting the application, and the application was talking to the database, incrementing this number, just to how many times it has been seen. The host name stayed the same every time because we only have one web instance. So let's call some havoc. I'll delete the database, and I'll delete the web application. Now remember, Redis here is configured to use a GlusterFS Docker volume. And in the ordinary situation, I kill this database, I've just lost the data that I stored, right? Especially if it started on another host. But what we'll see here is just by a matter of chance, Rancher had started this up where Web 1 is on the host that the database used to be on, and the database is now back on 03. They're both coming up. And they, of course, are going to remount, the Redis database will remount that Docker volume from the GlusterFS. And just to show you that these have moved around here. And we'll go up back to our application. And if things work correctly, we would see that this number continues. 4, there we go. So 4, 5, 6. The data that the database was writing to on the file system was replicated to this other host and then picked up as soon as that database started up again. So let's cause a little bit more havoc. So we'll stop the Redis database. And then we see this time the Redis landed on the first host. So again, different host. In any ordinary situation, the data would not even be available on that host, but we have the GlusterFS running underneath of it, and the data is replicated for every write. So now we continued on from 7, 8, 9, and 10. So let's talk a little bit about Docker internals. And every time I see this, I think, I really want to tell this guy I don't think he's using the circuit board right. But that's kind of the same thing with messing around too much inside of Docker itself. You can do this, but we're not going to get too deep in some of that stuff. But we talked about storage drivers. What are they? They manage. Remember that graph I showed you with all the layers that come in? They manage those local layers for containers. That's what the storage drivers are really doing. These are different from the volume plugins. The volumes are data that you want a container to write to. The storage drivers are the container layers themselves, right? And by default, there's it's a copy on write implementation, and Docker debuted with AUFS as the implementation for that. So every time a container wrote to a base image, it would create a new layer, right? And then all the containers would use, or the container would use all the data in that layer. So there's some considerations with AUFS though, is that, while it's stable and mature, it's not included in very many distros, and Red Hat had an issue with that in particular because their policy is to only use things that come in the kernel, and AUFS was not a kernel compiled module, and it's not necessarily as fast as some of the other solutions. Some solutions are through other driver options. Overlay FS is something that is up and coming, and it's kind of, I think a lot of people poise it as the next replacement for the default, right? Overlay FS. But there's other options here. You can keep using AUFS. There's BTRFS. There's Device Mapper, which is often a replacement that's used often for AUFS, especially on like Red Hat hosts. VFS and ZFS. I think the ZFS option is interesting myself. ZFS is something I've played around with a lot. By chance, Rancher had actually done a write-up. At this link, you can take a look. It's very easy to get ZFS running on a Rancher OS and then using that as your storage layer for container layers. There's some benefits there. I'm not going to go too much into that, but it's an interesting option. So there's definitely choices here. So here's a chart. This kind of comes from the Docker documentation. They show some pros and cons here. I don't agree with all of these, but it's a good place to start if you're trying to decide, do I need to change my storage driver considerations here for your needs. As we talk about some of these internals for Docker, we've been mentioning cgroups, which is a kernel feature. There's four main areas here when we talk about C groups, and this is the things that Docker and containers are leveraging. One is memory C groups, and there's the ability to put hard limits on memory that a process uses inside of a C group. And if that hard limit is reached, the process is killed. It's terminated immediately if that process exceeds the memory quota. Another option is a soft limit, which actually doesn't kill the process unless there's contention on the host, and then the processes are killed in order of priority based on how much over their soft limit they go. So the more they go over the soft limit, the more likely they will be killed, which is a nice trade-off in a lot of cases. There's also CPU C group, which has a few options for specifying how you want to manage resources between containers and any process running in a C group. One of these is shares, but shares are really weights. So you can say, okay, this has 10 shares, this has 1 share, and it's just that the other one has more weight for CPU processes. They can both consume 100% if they wanted to, but if there's contention, then the one with the more weight is the one that wins. There is possibility, though, of specifying hard limits similar to like the memory, and this is provided through quotas using the fair scheduler that's available in the kernel. And there's also the possibility of pinning a process or a container to a specific CPU if you want to give dedicated CPU to that container. Another thing here that's often asked about is, okay, how do I limit I/O? And in C groups, again, there's the ability to do block I/O management. So you can give, again, weights for devices. So this storage device has more weight for this container or the other. You can do this via devices, or you can do it within groups of containers and processes. But you can also specify specific, okay, no more than these many IOPS or these many bits per second for this container. And then I mentioned earlier, we had some talk during the breaks about the difference between Docker kill and stop and Docker pause. Docker pause actually freezes the process right where it's at. So it preserves all the registers and then the heap and the stack and everything right where it's at, and then resumes it when it's done. And that's a C group feature. That's something that the kernel provides. And processes are unaware of that. I'll get into a little bit about some of the things to think about when using Docker pause for best practices, because if a process is unaware, you may not necessarily have consistent state on disk. And that's often seen because some buffers may or may not be flushed at that point in time. So I won't go too depth on this. This is all of the ways you can specify this at the Docker run level. So you can set memory hard limits, -M, memory reservations, the CPU shares. You can limit the CPU quota through the fair scheduler, pin it to specific CPUs for dedicated CPU, and the block IOs and those sorts of things. There's a lot more that you can get into with the documentation that's available at that link, but this is the high level as far as what you would probably use in most cases. So we'll move into the best practices and considerations when using Docker. So this is a little opinionated, but some use cases are build environments. I think that's a lot of where people start, when using Docker. Is I just want a consistent build environment for my team. I don't want to have everybody to install all the same packages every single time from scratch, right? But as you, I think, mature, you can then start using Docker as the deployment artifact itself. And this obviously requires a runtime environment that supports the containers. So that's more of a big architectural decision as far as a product or service goes. But there's also an option here of using it as more of a real-time development workspace. So if you've ever heard of Cloud9.io or C9.io or anything like that, they have a really interesting way of using containers. You log into C9, and it's a web-based UI, so IDE, so you only get so much functionality there. But you have a live shell, and that's running inside of a container. And when you leave and you don't come back for a while, they'll freeze it, they'll do the Docker pause, and store that, and then when you come back maybe a week later, they'll resume it right where you left off, your whole terminal command line. A little bit different than build environments because it's more of a live workspace. Some of the use cases here are the multi-tenant hosting. You can have a lot of different tenants running in their own dedicated instances and all these containers without having to spin up all these VMs to do so. And as I mentioned, kind of pushes us into the realm of microservices because we can think really small in terms of what we're running in these containers because they only need the dependencies that they require inside the container. You don't have to load up the whole host with all these dependencies. And another option here, and I'll talk a little bit more about this in a few moments, is running a VM in a container itself. Seems a little bizarre, but it's actually possible using KMEU, for example, or EMU or KVM. You can run virtualization inside of a container and use containers as the packaging mechanism. Some misuse cases that I think are out there are using them for very high security workloads. I mean, like insanely high, because of the shared kernel and any sort of vulnerabilities in the kernel. There's already been proof that you can escape containers in certain circumstances. It's usually due to kernel or Docker daemon bugs or those sorts of things. So that's something you would want to consider for sure. It's also high stability workloads, because it's the same thing. A kernel panic caused by a kernel bug triggered by one container would bring down all the containers on a host. But honestly, that's not that much different than a hypervisor crashing, right? Because a VM triggered a bug in the hypervisor. I think some misuse cases are like for slow rate of change groups. They just don't really change things that much. Why complicate stuff if things are working really? But I think there's a hint there. If they need the change, maybe they should look at containers. And then really big containers, I think there's a lot of discussion out there. Are fat containers something you should avoid, or is it something you should embrace? And I don't want to be too opinionated about that. I think ideally, if you could, try to avoid it. Gigabytes in size, because you have to pull this across the network, right? And if you're trying to spin up a container really fast on multiple hosts, you don't want to pull that much data. And then also just using containers for cases they don't matter. But I think it really comes down to, depending on what your use cases are, what's the best decision for you? That's what I would stress. Try not to take too much of the opinions out there, but figure it out for yourself in your own use cases. So when it comes to best practices, though, when we look at building, we talked a little bit about this today, Docker files, just use them unless you have something better. I've seen people doing the manual steps, like I did earlier, just as a demo, as almost their continuing way to do container builds. And it's just, you lose the repeatability, you lose the consistency, and it's nearly as fast just to create a Docker file and then do Docker build. So I don't see many reasons why you wouldn't want to. But then when it comes back again to the size and space of containers, it's really good, if you can, to avoid bringing in stuff that you don't need into your container. And so now we're starting to see a lot of movement towards lightweight distributions that are in container, like Alpine Linux. And in fact, Alpine, I don't want to say necessarily it was acquired by Docker, but they're like really close now. And now Alpine's starting to become like an official image that Docker themselves support. Another best tip here is if you are building from a base image, pin it to a version, because you don't want that change, the immutability. Every time you build a container, you don't know what one you're basing yourself on. So it's good to pin it to an immutable tag. And then just again, from a best practice standpoint, think small in what you're building in containers. What are you bringing into them? Do you have to bring it in? And think reusable. Can I reuse this as an image for other containers? And then what is this container doing? Is it providing a service? Is a good approach there, especially if you're trying to push towards microservices. From an optimization performance standpoint, we saw a little bit about this with the ampersand thing to concatenate multiple commands together into a single layer. But that capability, as I was alluding to earlier, that every directive in the Docker build file is its own layer, can actually be used to your advantage. So if you know you're going to be massively building dozens of hundreds of containers, you can, for example, use the Docker, the run apt-get update on a single layer, and then all the other layers will not have to do the apt-get update. They'll actually share that cached layer between all of them. And so that can speed up builds quite often, as you saw that it takes 20, 30 seconds to do an apt-get update. And then we talked about the layer minimization. The immutable tags, I touched on a little bit. You want to try to make sure that the latest tag is okay to be moving around always the latest, but it's really good practice to have a version tag pinned to a specific image, and then that's never changed, so people can have something reliable they can depend upon. And then I think we talked about too, the Docker run will not repull an image, so it is good practice if you are using an immutable tag to always make sure you do Docker pull before Docker run. That actually had caught me, as I mentioned when I was creating these demos, because I had forgot to pull. And then we saw that the containers are not destroyed as soon as they exit. So one way to deal with that is to always make sure you do the --rm, but the --rm will not delete the volumes if they're not shared. So we saw a little bit of that. If a volume has been created by one container and you use --rm, it will persist. I actually think I reworded this wrong. So if the volume is shared, it will not delete that shared volume. And so you can have this accumulation of the container images and the container volumes, especially unnamed ones. So that's something to watch out for in a runtime environment. From a network standpoint, I mentioned this before, the user-named networks are the new way of doing things instead of the links. And so all the containers are supposed to link and communicate through a shared network with the Docker network create. You don't have to worry about this in Rancher because it creates it for you through the IPsec tunnel. And from a configuration standpoint, it's good to ensure that your logs, and this is really common practice for anything, right, is make sure your logs are in a separate partition, because if the logs fill up, you don't want it crashing everything else, because even the OS can't get enough space. But because Docker has all these images you're pulling in layers, that's the same thing applies to that. It's best practice to have your layer stored in another partition as well too, so that way you don't crash running containers if somebody pulls a massive image and then consumes all the storage on the local host. Then you can specify that with Docker ops for your Docker daemon as well. From a best practice standpoint, I started talking about this. The Docker pause uses the cgroups freeze, and so the process inside doesn't know that it's going to be frozen. And so it may leave the disk and the files in an inconsistent state, which could be problems depending on your backup, right? Because when you restore it later, it'll be viewed as corrupted. A good practice here for well-behaving processes is to tell it you're going to stop it. So the Docker pause used to send sig stop, which doesn't kill the process. It just tells it, hey, you're going to stop here in a second. You can do that manually by docker kill-s equals stop. And so you can inform the process, hey, you're going to be stopped. If it's a well-behaving process, it'll do something to that signal, flush the buffers, those sorts of things. And then you can call Docker pause, right, to make sure that it's in a consistent state. Because Docker pause will ensure things are consistent, but not, it doesn't ensure the integrity, right, of the data. And then provide your backup mechanism, whatever that may be. You can export a Docker volume, various things there. And then when you resume it, do the opposite, unfreeze the process, and then tell the process, hey, you can start back up again by issuing it a signal, continue. And again, I keep stressing that these have to be well-behaved processes, because if they don't listen to these signals, the stop and the continue, they won't do anything to them. From a security standpoint, I'll show you this command in a second. There's a container called Docker Bench Security, which will actually scan your configuration files on your Docker host to ensure that you have set them up with some best practices for security. There's also tools out there to scan the container contents themselves, because one of the interesting things about containers, right, is that you're packaging these libraries up in the containers. And so if you have a patched library in there and then a new vulnerability is found, you still may be using that old library when somebody else pulls that image. And so there's a stat out there for Docker Hub. Something like 70% of the containers out there have unpatched vulnerabilities, shell shock, Heartbleed, SSL, all these different things from the libraries that they're embedding inside the images. And so these tools like Claire, and there's a new tool called Docker Security Scanning, which used to be called Nautilus, will scan through all the layers and figure out, okay, what libraries are in there and are any of them susceptible to known vulnerabilities. One best practice here as well as in the containers, I showed you I was doing run from a container and I was running in root by default. That's what Docker does. That's not a best practice, although you don't really have to worry too much about escaping the container unless there's bugs and things like that or issues in the Docker daemon. You still have processes running in there. So if someone were to, for example, escape out of an Apache daemon running inside the container, they could have root access at that point and affect everything inside of that container. So it's best practice to run specific users inside of a container to prevent things like that, just like you would normally configure a physical host. One thing to also think about is avoid users actually interacting with the Docker daemon itself, because they have to have root access. If they don't have root access, you can specify a Docker group, but that Docker group is just as good of having root access for those users, because the Docker daemon has root access, again, exposing vulnerability. So it's a little bit better to ensure that you have some sort of container management on top, like the Rancher UI, because that can have access controls, and nobody accessing the Rancher UI has to have root access right on the host to then start and stop containers. So that's a good way to protect your host in that case. From a default Docker bridge standpoint, security best practice here is actually disable what's called inter-container communication, which is on by default. Basically, it's just allowing all containers in the Docker bridge to talk to each other. You can pass this in through the Docker daemon ops --ic equals false. And then what happens with bridge 0 only is that when you start up a container, it will open up a port between the containers and the Docker bridge with what's been exposed in the container itself. So if you did the expose directive in your Docker build file, it'll open that port up to other containers in the bridge. I wish they had done this for the user networks, but it doesn't work today. And in fact, I'm actually thinking about opening up a pull request for that because I think that's a nice feature to have. It's a lot of extra security for not much because usually you'd be using export directives anyway. But the problem with the user networks is they don't support the linking. As I mentioned before, only Docker Bridge supports that. And so you really can't use the ICC file, so you can't get any containers talking to each other. So let's show you the Docker Bench security tool. So this is just as simple as running a container. Docker run. We have to specify the host network and the PID host. I'm not going to go into much of what that is. Cap add adds some additional privileges because this scanning tool needs extra privileges to see what's going on in the host. And we're going to mount some directories for Docker and the system into the container. So again, this container can scan these. So I'm piping it through this PV command to slow down the output. That's all that is on the end there. And so it comes up with a banner. We can start seeing some of the interesting things here. It looks at the host configuration. It does exactly what I said. It's looking for different partitions for containers, looking for updated kernel versions in Linux, removing services, those sorts of things that aren't necessary. Keeps on going, looking for different configurations that may be set up. So there's actually a possibility of setting up Docker to have remote Docker. So one host can control a Docker daemon on another host. It's not set up by default, but some groups do that. And so they look to see if that's protected. Especially in that case, you would want SSL protection in between your two hosts for Docker remote. So it's looking to see, okay, do you have TLS set up for that? It's looking to see, have you correctly set up file permissions for things like the Docker socket, which is actually a file, docker.sock. Is that protected in a way to make sure that nobody can access it? It's looking for those sort of things, file permissions. And then it actually starts scanning some of the images at a low level. So as I mentioned, it's looking to see, do you have any containers running as root? And in this case, I did, the one that I created, so it warns me about that. And then also looks for other Linux security features like AppArmor and SE Linux that can be leveraged, but are not configured on this host. And then a few other options here that'll spit it out. So just in summary, though, this is a really great tool just to scan your host. That if you're running Docker on it in production, to see, okay, what may be misconfigured, or what sort of things have you may not even thought about that you would want to protect against. So now we'll get into Docker Pro tips. So I've been alluding to all day. These are really just tools and sort of things that I've discovered out there. So one of these is more of a pattern, really. I demonstrated this earlier. I like this a lot. I'm calling it lazy installation of applications. Basically, create a bash alias, and then inside of that alias, give it the Docker run command, and then pass in the parameters to that. And what that allows you to do is basically install every command on demand when it's used. And the interesting thing I think about this is like, what if we had a distro that did this? Every curl, wget, every dig, everything as you needed it was installed as you needed. No longer needed to do apt-get. Right, just on demand, it'll run this in a container. You can also do this, of course, without aliases, just as a bash command. So another thing that I talked about a little bit earlier today is the Docker 0 default network uses 172.17.0-16 as its default network. And this actually conflicts with the current Cisco WAN configuration. In fact, I think it's the Quay instance that I was demoing earlier is actually inside this subnet. So that's the first way we found out, is because I couldn't pull from images from that. So you could, inside of Cisco, register your own subnet, and I've been finding that's extremely painful. That's why it's up here in the hard section. But it would be necessary if you want direct routable IPs inside of a container, which honestly, just a matter of opinion. I think you can get away from doing that in a lot of cases by routing through a proxy, like HA proxy, like I showed you, and just use private IPs for your containers. Another option is to tell Docker that you want IPv6 inside your container network. And I think they use the default subnet here too, but I haven't played around with it too much. But this configuration sets up a dual stack bridge so that containers are only using IPv6, but then the Docker bridge itself is mapped to an IPv4, and it does the v4 to IPv6 translation for you. Though an easier path to avoid this conflict is just to set your default Docker network to a non-routable subnet. In Cisco, we have 10.0.0.0.20, which at least for now is a non-routable lab subnet, so no one else is going to be using it in Cisco. And to set this up, it took me a couple of tries to figure out the exact syntax, but you set up your subnet, and then you tell it the bridge IP that you want within that subnet. And so once you set this up on your Docker daemon ops, you can get this up and running. And in more of a production environment, you would want to subnet this further, so that way those container networks, as containers you want to speak together, and you're using the Docker user networks, each one of those should have their own subnet off of this, right? So they won't conflict with each other if you're trying to route between them. Another thing here, and I'm just bringing this up because I thought it was a kind of a neat tool that I ended up using, follows, so it's kind of that pattern I was talking about before. You could alias this. It's just dig. It's useful for the minimal OSs that don't come with all the tools, like dig, for example, for troubleshooting DNS and things like that. Rancher OS does not come with dig, and that's where I use this. But I quickly found that there's a catch-22 with this. If you're trying to troubleshoot the DNS issues for pulling an image, and you want to use dig to do that, you can't get it. So that was kind of a thing I had to work around. But another kind of pro tip here is the imagelayers.io. If you've not heard of this, it's a really interesting site to go to just inspect external hosted images. So you can go to imagelayers.io, and it analyzes the image layers for all the publicly accessible images. And if you're doing open source projects and stuff, you can create badges as well too. And it's very similar to what I showed you before, Docker history, and then what Quay will show you is the history of commands that composed all the layers for that. The shortcoming I found with this is for some reason or another, it does not work with all images out there on Docker Hub. Some of them just don't come back with any data at all. Here's a screenshot of it. This isn't a demo. But there's basically 6 columns here, and you can compare against each other multiple images. And so the bars that reach across are shared layers. And so we have the 2 first layers are shared by all 6 images, and then these 2 layers down here are only shared by 5 of the images. So it's an interesting way just to see, okay, how are these layers being composed on public Docker images? And you can, of course, see down at the bottom the exact commands that they're running in the Docker file. So we talked about optimizing images. There's a tool to do this as well too when you want to squash layers. I would say this is a last resort. It's kind of like the nuclear option. It's best to do it in the build file if you can. But it's a GitHub project. It's its own image. Another person created an image for you. And it compacts all the images together. It's an interesting way to kind of fix security goofs if you can't rebuild everything from scratch for some reason. Because kind of like Git, you have this commit log of layers. And if you were to insert a private key, for example, and then delete it in another layer, it still exists. It's still in that layer. It's just that second layer removes it from your view. So kind of like Git commits do, you can still have that in there. So if you really want to get rid of it, you'd have to squash all those layers together to get that delta where it's been deleted, that private key. So you can use that for that. But as I mentioned, it's really better just to use the Docker files and optimize there. There's 2 ways to specify it. You can say, all right, I want to use the Docker squash based on the last layer from the from directive in the build file, or I can say I want to specify specific layers such as the root, and I want to squash everything, right? It doesn't really save you space, but it just saves on that layer count and the number of layers you might have to look through. Another tool I like here is called DocViz. This actually broke with Docker 110 as of December. They made some changes. There's a PR open that the author has, and he's kind of waiting for an upstream PR with Docker to get it fixed. But when it does work, or if you're using something below 110, you can create graphviz.files, and so you can use this in your own tooling and stuff like that and visualize these. Or there's a text-based view, which I'm showing here, which shows you all the layers and the hierarchy that's composing your Docker images on your host that you've pulled. Another image that I think is really useful is this one called Docker Cleanup. So we talked about how the containers, when they exit, are not removed, volumes are not removed, those sort of things. This is something that will continue running and do that cleanup for you. So anything that's unused, it will eventually come along and remove it for you. A very nice tool for that. So it'll clean up exited containers, unused images, which can usually take up the more space, is just the unused images that you don't use, and orphan volumes. It's completely configurable. You can say, I want this to run a specific time on specific images. You don't have to say everything. And it's also already available in the Rancher catalog as a janitor catalog item there. So that will go and clean up all the images and stuff pulled on the host. And it's just a simple Docker run to get it to work. There's also a base image that's interesting. I mean, this is more of just to put it out there for your information. It's really up to you to decide if you want to use it. It's an opinionated Ubuntu 14.4 base image. And what they've done is, as I was talking about earlier today, there's a PID1 that starts in every container. Now, PID1 is usually an init process in Linux. And that init process is responsible for cleaning up any orphan children processes. But that doesn't happen in a Linux container if that PID1 process doesn't know to clean up child processes. So what they've done is they've tried to address this, what's known as the PID1 reaping issue for that. Because what can happen is eventually you run out of PID numbers on a host and no new process can start. So they've made sure that bash is always running, because bash actually does proper cleanup of child processes. It's always running as the initial init process, and so anything else you build on top of this would be cleaned up properly. I've also done a few fixes here for what they view as app patches related to init as well too. They've added into this container image for you a syslog daemon, a cron daemon, all these things that don't come by default with a default image. And they've also put in to the cron entry some log rotate and a service supervision service called RUnit. Some of you may be using system, Supervisor D, for example. Their opinion about RUnit has some interesting points to it, so take a look at their GitHub page. And they also added an SSH server, which is arguably a good or bad practice. They view it as a good practice because, as I mentioned before, if you do Docker exec, you have to have root or root-like privileges. They view it as a way to get around that because you can SSH into a container and then do things without having to run Docker exec. It's kind of an interesting view on that. But really, it's a big container, not huge. I mean, it's not a gigabyte, but it's considered more heavyweight than others, like Alpine. And so it's really up to you to decide, is this too heavyweight for me? Does it even fit my use cases? But it's definitely interesting, I think. And then I talked about this earlier. Running a VM in a container is an interesting idea. I think a lot of people would balk at it initially, but Rancher has a project set up on this. So they have packaged up the VMs inside of a container. So the container itself is the mechanism to move around VM images. And so it allows you to have full virtualization and emulation on a host that's also running containers, right? So if the containers are just not enough to do what you need to, you can use something like this. And there's a package out there for this. So the interesting thing about it, compared to like OVAs and all these other things that you may use for VM images, is that you can leverage the container ecosystem tools, such as the build tools, the scheduling tools, the quotas, the networking, storage. Arguably, you get a lot of that, of course, with VM infrastructure, but you can apply the same things that you would to containers to the VM without having to have two different ways of doing it. And you can also run this, for example, from the Rancher UI and the container management, as I said. All it requires is for the kernel that the containers are using is to have KVM compiled into it, or QEMU if you're going to use emulation. And no KVM user space tools are required on the host. They're just inside the container. So it's an interesting approach, I think.